Hi all, welcome to this session. Let's start the session. First of all, those of you who have attended the last session, if you have any questions, we can go through them. Then we'll start today's session. Thank you. If you have any questions, you can post in the comments as well. Thank you. Okay. No questions from the last session or anything confusion or can you start from revising architecture of GPU a little bit before coding? Yes, not in much detail, but we definitely will go through some parts that we are gonna like uh, see the codes of them today. Okay, so let's start from where we left off actually in the last workshop. So little revision to the previous workshop would be great. So so let me share my screen first. So okay, so let's start this session, and so those concepts, I guess, will be somehow uh, will be covered in today's slides, which will go for like before the coding one, because in the last session, the thing which we were coding, there was no, I guess, the micro arc level things or that thing. Okay, um, so we'll go a little bit uh, over this micro arc things and a few slides before diving into the code. So on the higher level, the streaming multiprocessors, if you could see them, there's instruction fetch. This is a high level diagram for a streaming multi processor. So this is the simplified version. Obviously, we are not gonna uh, discuss the details of it or in depth actually, because this is again, this workshop doesn't allow the time to be the main fact, which is the time is the main factor actually, which is restraining us from going into depth in this workshop. So we'll have like a high level picture of that. Uh, if- I guess you all know, maybe if you don't, we have announced the GPU training program, which is a 5 week long program in which we'll be covering all these concepts in quite a detail, uh, with each module and with each module being coded live and with a lot more of features. Because in this workshop, we can't just go through everything. Uh, so that training would definitely cover a lot of ground, starting from AI workloads, for instance. In this workshop, we covered only three types of AI workloads, and that two was those two were like covered only. We covered only the definitions and just a little bit of detail. But in the training, we will be covering like five of those AI workloads, and also with the like quite a bit detail and examples, and you doing the assignments and all that stuff. Uh, so there will be more understanding on that part as well. Again, on the GPU microarchitecture, there will be more details in terms of microarch thing, with each module being discussed in a single session of like 2 or 3 hours. Uh, and then in terms of coding, we will have more time actually to deep dive and actually live code that microarch. For the training part, we will be designing first the microarch specs for each module, defining the ports and all the details and the features, and then we will delve into the coding part. But for the workshop, it is not possible to go into that much detail with every module's microarch spec and all that stuff, because it will take a lot of time. Um, let me share link. Uh, okay, I'll pin the training link maybe to this. So okay, so this is now a top level streaming multiprocessor topology, or the microarch, you could say. So obviously, because it is there would be some instruction coming in, so we will need to have that instruction fetch, and I catch that, and then we'll decode that instruction, and then uh, scoreboard and the warp scheduler actually does that thing to route those instructions to different warps, and then through warps it goes into different threads and the lanes in the SIMT codes actually. Uh, so for the register files, actually, here you could see that it is like bank. So bank, what is the bank register file is that uh, you could say that you have divided that whole kind of a register into different portions, and each those portion is being allocated to some specific lanes, right? Uh, in that way, those lanes can communicate with the register file, and the register file can send the operands to the lanes, and so there will be a memory unit or a LSU unit, and then there will be write backs back to the register file. So this is just the high level thing, not the you could say very going into my details. So in this actually, when you see these SIMT ALU lanes and the register files or the warp schedulers, so these ALU lanes are like multiple threads, right? They could have 32 threads or 32 lanes running those uh, this- like in a single instruction, multiple thread or multiple data type configuration, and then those multiple threads actually communicating with bank register files, so they do not have the dependency with other you could say ports or the banks. And again, there is scoreboard which will be there for handling different type of conflicts and all that stuff. So this will be just the instructions flow. Just the base one. So in this one, the execute unit is a multi-stage SIMTL, you with register file differences and all this stuff. Uh, Bank register file, which will be communicating with different lanes and all this. Okay. Uh, so so lanes. Uh, you could see the lanes will be like these parallel kind of stuff. With, okay. So each having like their own functional units or the ALUs, you could say, to compute those instructions and give the results back. But as we have discussed in the last session as well, that the main computation done will be like the matrix multiplication, in which the data is quite independent, and then computations can be performed independently. So we can send the data to multiple function units in those lanes, and then calculate them in parallel, and gets the result. So in that case, the latency will not be like isn't like optimized, but the throughput we get is quite large. Okay, so the throughput is the main focus here. Okay. So one of the things will be the warp scheduler, which will be scheduling the different warps. Actually, uh, means so those warps have like different lanes inside them or different ports inside them. So this warp scheduler does what it really sees that which warp is available and sends those instructions to those threads. Actually. Um, and if, for example, in this example, if you could see the image here, so warp one is called because it is waiting for some memory stuff. So there is a latency, right? So there is a latency because it has to wait for some memory instruction to complete. So latency is there. But what happens is that next instruction comes in, and because warp 0 is ready, because it is now doing something or its codes are available, it can send that instruction to warp 0. Uh, and warp 0 again calculates its result. And when you see from like in terms of unit time, the throughput is actually a lot more because there are different, uh, quite a lot of numbers of cores or threads working in parallel to compute those results. So, so if you have gone through some processor design, or you would have definitely seen the scoreboard stuff. If not, we can discuss a little bit here. So the scoreboarding actually happens in processors actually to eradicate the conflicts between different registers. Because if some register is being in use for the computation and the next instruction comes in to update that or read that, uh, so there has to be some module or the hardware that needs to check that, right? Otherwise, if if there is some register uh, that gets updated before it is being read actually, so it will cause the wrong data to be computed, right? So let's take an example of the scenario. So let me, so let us open this. So for instance, if you are using R2 as a destination register to some instruction, right? For example, this is a add instruction, right? So R2 is a destination register. So this instruction is in ALU calculating some result, right? So R2 is being calculated right now. For example, if you are adding R1 and R2, R1 or R3, for example, R1 and R3, for example, you are calculating this add instruction. And then another instruction comes in after this add instruction, which is using R2 as the source. For example, it is using R2 as the source and some other instruction as a destination. Okay. So if this R2 isn't being calculated and written back to the register file, right? So it means execution unit or ALU has to calculate the result of R2 and write it back to the register file, right? So there could be some register file in which R2 needs to be updated. But this instruction comes in and R2 isn't being updated in the RF register file, right? What would happen is you will pick up or read R2's old value, right? For example, it at time one, it is calculating this computational, right? And at time three, for example, or clock, you could assume that this is the time, okay? So at time three, it will get updated into the register file. But at some time two, or the clock cycle two, this R2 got read, okay, from the register file. So what would happen? At time two, R2's values for example, was 4. Okay. So you read 4 from the register file. But at time three means after 1 second you have read that R2. R2 gets updated with the now the new value, right? The instruction that was in flight, right? So it gets the value 10. So ideally, to function it correctly, the instruction that was proceeding this instruction has to get R2 as the 10, right? Calculated right. So this dependency or the conflict, you could say, or the hazard in technical terms, is being handled by the scoreboards. They detect it and then they apply some kind of a remedy to it, maybe stall the processor or forward something or not in processor terms. Okay, but for the GPU, if we talk about now the GPU's scoreboarding stuff, you could for our workshop, it could be quite simple, right? So what does it do is it issues the register that is being in use. Register file, for example, it issues R5 as the destination register. So it simply marks R5 as busy. Okay. So it marks R5 as busy. And then it keeps on checking. Uh, for R5. For example, if the instruction 2 comes in and it requires R5, register 5, right? So what it will do is it will stall. Okay, it will stall, uh, or it will, you could say in simpler terms, it would stop the pipeline. It will stop that instruction because it would say that R5 is already busy and the instruction 2 will get access to R5's data after R5 is being written back to the register. Okay, so in step 3, if the R5 is clear, and it will get cleared only after it is being written back to the register file. Means now register 5 R5's value is being updated in the register file, and now instruction 2 can obviously access it. So now the scoreboard does these three steps, three things to avoid these things, or the conflicts, the hazards, right? First, it issues and marks that and keeps the record of that register. Second, it if some instruction requires that register which is already busy, it blocks that or stalls the instruction, and then it checks if the R5 is being cleared or written back, right? And then lifts the stall, and instruction 2 uh, gets into the pipeline for the computation. So this will be the scoreboards thing. It will be doing the. So we are saying that bank register file, maybe in the last session as well, and for now as well. So what does that mean? So it means that, so if you see on the left side, so this is in a whole register file, right? If you combine this bank 0, bank 1, bank 2, and bank 3, this is a complete register file. But you divide it into different banks or portions, if you could say, and then each portion is assigned to, for example, one lane, right? For example, bank 0 is handling lane zero's data. Okay. For example, then bank 1 is handling data of lane 2, and then lane 1, lane 2, uh, and so on, right? So you have banks which are divided into the different lanes, right? For example, if you see this bank 3 here, so it is connected to lane 7, and then again you could say you could see here it is now going two way with lane 6, and then connected with lane 5, uh, and then the bank 1, right? So this kind of banking or the interleaving actually provide more ports and also avoids conflicts, right? Because if you are gonna so this bank 0 has its own registers, right? Okay, so if lane 0 is communicating with bank 0, it means it will get its data from bank 0 and write it back to only the bank 0. So the registers available, or the portion of the register file available in the bank 0 is not different lanes are not like uh, register file multiple times, right? Otherwise the conflicts comes in. So it means those 8 lanes are now divided into these 4 banks, and now can in a distributed way they avoid conflicts. So we are not going much into the Roadster parts. Okay. We are not covering divergence, I guess, for this one. So, okay. So for the SM to actually, you could say communicate with different kind of external things. First one is just the L2 or the global memory or the shared memory, where the load store request actually goes on, and then to the different iCaches, different iCaches, the iCache, because the PC request comes in and the instruction data um, actually instructions actually come into the streaming multiprocessor, and then with a different debug interface, which is also for the debugging purpose on the hardware side. Uh, Okay, so maybe we'll go to the coding side a bit. Let me see if I missed something into this slide. Okay. So on the computation side, uh, how the lanes operate, maybe you could remember from the last, I guess, session where we were designing uh, a pipeline kind of a ALU or pipeline kind of a lanes, right? So what was that was so it could be divided. That lane could be divided into different pipelines, right? For example, in the example, if it is divided into three-stage uh, ALUs, for example, so what would happen is so EX1, EX2, EX3 are the stages name, right? So in first stage, what it does is fetches data, for example, from the register files, right? And then it computes that data and then gives the result back, right? So in three stages, it could be divided into three stages, right? To improve the maybe uh, frequency or divide the workloads, right? So if eight lanes, like or the threads are doing this, for example, they could handle eight uh, elements or the numbers in a single instruction and calculate it in a pipeline way, right? So this is how the pipelining actually works. Um, so if I could see any questions, can you share the link for the training? Okay, I'll pin that to the chat. If you would see, will be given access to those slides. Yes, at the send. Yes, I'll send those slides at the end of the session. What about the one? Did I understand this question? What about the one? What was the question? Can you explain that question? Maybe one which was. And what are those? What about the interconnection of banks? Yes, I was referring to this question. What about the interconnection of banks? What are those? Okay, yeah. So you could say that bank zero and bank two are interconnected, and bank one and bank three are interconnected, right? So yes, uh, so they are connected actually to handle different lanes data, right? Uh, so these are sorts of like interleaved memory banks. Okay, so uh, s- so now let's go to our diagram, which we are gonna like uh, see the diagram actually, which looks like micro arc thing. So let me give a second so that I could pin the trainings link in the comments. I think there's a question there. So I have to copy that. So you could apply at this link actually, which I have like sent in. Yeah. Let me know if you could see that link because we were having issue last time actually. So I pinned that link. So let me actually build that image so that you could now make more bigger picture of what we are gonna code actually in what that specific uh, component actually fits in that bigger picture. So let us do that uh, here. Maybe. So I am just slowing down and doing my pace intentionally because I wanted to build that micro arc image so that everybody is in aligned with what we are building right now, right? Otherwise, I could have gone through a single image, and again, some of you could have like missed something. So let me use this if it could. So yeah, so this is so this will be registered. Let me first uh, build these and then we could go through each of them. So see that. Site is showing to me. Okay, so if yes, it is a website and you have to like apply that here. Okay, there will be apply button at the end of the page that you could use to apply, right? But make sure one thing that uh, apply if you want to apply it earlier because if like the seats are filled then the applications like before even the deadline as well because we have to see our capacity and uh, to have only those many number of attendees actually which are being like managed well and could learn in a better way. Okay, so thank you. uh, so yep, so there would be lanes of the threads in here. So these lanes could be divided into different functional units. So just building them. Just excuse me for my drawing or painting skills here. So similar will be the case for the other register file. So so okay, so this is gonna be. So now what happens is so uh, let's treat it a bit. So you could say that these are the registers or the register banks actually, and this is also the register or the register bank, which is like interacting with the with those lanes, right? And these lanes will have like different units. For example, FP32 for the floating point, for the uh, integer things, for the different ALUs, right? And also they are being like pipelined. Uh, so I guess so. These are the lanes, and and those register files again. The banks will be doing that, Okay. And for overall like scheduling here, the warp schedulers are there. So those warp schedulers will schedule those instructions coming into the different threads, right? So these are the warp schedulers. So each warp which we say you could say that it is an independent type of a unit. So it controls it has its own instruction like coming uh, from the from you could say outside. So that gets routed into some lane, and then that lane actually uh, you could say that lane then actually computes that and writes back to the register file or whatever the register it needs to update, right? So in these warp schedulers, what we get is what we get is the like the uh, you could say the PC and the instructions, etc. Right? So and instructions and like that. So before that, the warp scheduler I've seen in the diagram a bit little bit of time ago. There is an instruction fetch and decode part as well. So now we will like go to the code side. If you have any questions before that, we can definitely handle those and then can go to the. Let me know if you have any questions on this. The code sequence, what does it mean? Uh, can you explain a bit? If you could write the comment actually the code sequence because I didn't understand that code sequence. So okay, so this is a good question. So we will be building these lanes first that we built in last time as well. The SIMT ALU in which we built 8 lane ALU, right? Means it has 8 lanes, and then we'll build the register file per lane, right? Which will be banked and that register uh, simpler as 4. For the sake of workshop, we will be like making it or we'll designing it in the most simpler way because we cannot uh, in this time we cannot have like a very complex or feature filled core, we cannot go much into much details, right? So we'll go over through the different codes to see what's happening there uh, and understand those codes with this and try to match with this diagram, right? So any other questions? Okay, if there are no questions, then we will move to the code part. Let us take just a 5 minute break. Let's come back in 5 minutes, right? Thank you. And then we'll start on the code side. Just a 5 minute break. So, okay, am I audible? Anybody can confirm that I'm audible? Okay, thanks. So, start with the coding part as well. Okay, let me log into the VDA playground and just a So let's start with the SIMT LU. From the last session, there were a couple of confusions around the SIMT LU. So I have simplified this code a bit and removed the pipelining part out of it so that we uh, do not face that kind of confusions here. So let us put this SIMT underscore ALU dot create that file in this way. So let me know if the font is visible to you guys. So otherwise, I'll try to have it centralized and have some bigger one. So let me know if you could see this one properly. So if you could see the font and now clearly, okay. So let's go through this. So this is very simple ALU actually. There's no pipelining. I've removed the pipelining stuff. Now it's quite simple. It is just like we have different ALUs which are equal to number of lanes, right? So, for instance, so this takes in operation A or B, sorry, operand A and operand B, and its data width. So, for example, if you want to have say 2 bits of operands, you could select using the data width, and then there are lanes. There are, for instance, if you want 8 lanes, you could set the lanes parameter as 8, and then you have active mask. As discussed in the last session as well, if you want to uh, mask some lanes, especially when there are branches, you want to like mask some of the layers, so that the result is not being computed for those layers. So you could use this active mask uh, variable, right? So what it would do is it would check if uh, the lane is active, then it will compute the result for it. Otherwise, the result will remain zero. Uh, So okay, so this is very like a simple code. So when the result is calculated, and again it depend on lines. So if we say there are 8 lanes, what does that mean? It would mean that we will have like 8 of these functional units, and we have 8 of those operands A and B, and then we have 8 of those results going out of the SIMT ALU, right? And the opcode is to 3-bit number. So So my question to you guys is, we have discussed a lot about this as well in our discussion today, maybe in the last session as well. So we have number of lanes equals to 8, right? Number of lanes are 8, right? So what why opcode is only of 3 bits? Why it is being like not divided into lanes? The operand A and operand B are defined as register blocks or something. Yep. First, maybe after this question, we'll come to that specifically in the register file thing. So why opcode is of 3 bits only for 8 lanes? Though the operands and the results, for example, if the lanes are 8, the operand A and operand B and the result are 8 times, right? 3 bits requires to represent 8 lanes to 8, so opcode covers all. No, the opcode, so opcode purpose is not this one. Anybody else? So opcode is defining the operation, right? Which operation to perform. If you could see here in line number 16, you could see that opcode has in opcode, if there is 0, we are starting those operands. If it is 1, we are subtracting those operands. If 2, we have and for those operands, and then or and or, right? So my question is, why opcode is of 3 bits? Because other are all data bits, and also they are incorporating the number of lanes. 3 bits for 8 types of operations. Yeah. So yeah, this is the most. Yeah, this is from Tilha. Yeah, this is the right one, because it names tells us. So what does its name is SIMT ALU SIMT. So SIMT is single instruction multiple threads, right? So single instruct what does single instruction means? It really means that there is a single operation, right? So single instruction is technically a single operation, right? Normally, so that single operation is operating on multiple threads, multiple datas, right? So that's why we have different number of lanes, or you could say multiple lanes, compute the data, right? For example, if we take this example, we have 8 lanes, compute the operands coming uh, from that single instruction. So it is only the single instruction uh, that has that data, right? But because it is single instruction, so the operation is a single one. So that opcode would have definitely only a single value for all of those lanes. For example, if the instruction was for the add, right? For example, if it was the add two registers and calculate the result and write it back to register 5, for example, right? So what would that mean is that the data coming from the two source registers would come to the 8 lanes, right? So it would be like lane wise data or thread wise data. So we would have like thread wise registers for these ones. So that data would be processed, and because now the instructions part, so all of the lanes, all of the 8 lanes in that you could say in this SIMTL, you have to perform the operation add. So that's why the opcode is only of 3 bits and doesn't depend upon the number of lanes. Its size doesn't depend upon the number of lanes. And the question is for the active mask, why we need active mask signal? So active mask signal is primarily needed to mask out the any lane. If any lane is divergent and we don't need it to compute the result, right? So we don't want some lane to actually compute the result and we want to mask it. So this is the way to mask it. We have the signal active mask coming into it, and uh, if you could look at the line number 15, it first checks for the active mask, right? So if the lane is active, then it would compute the results depending upon the opcode out of its operands, right? Otherwise, it will give the result 0. Means it is inactive, right? Lane is inactive. So that lane doesn't affect the result. So this is quite a simpler version of that SIMTLU that we looked at in the last session. Uh, it was actually pipelined, and by the way, that was also somewhat a similar, a simpler version from the one which we will be designing in the training as well, with more features as well. Okay, so this is the SIMTLU. Any question on this one? This is code for the SIMTLU. Any questions from you guys? If you do not have any questions, data width represents. So data width is primarily the size of the operands you want to calculate, right? Compute. For example, if you want to work with 32 bits numbers, right? To add 32 bits number, that means the data width will be 2 bits. For example, someone wants to like operate on 16 bits numbers, when that SIMT you will require data width equals to 16 threads for multiple data using a single instruction. So this is using so SIMT means single instruction, multiple threads or multiple lanes, right? Single instruction, multiple lanes or multiple threads. So it means there is a single instruction coming in, and we need to have. So from where this instruction is coming, it is coming into the from the warp scheduler, and then we have different warps, and then from those warps, it is coming into the lanes or the threads to be computed, right? So and we have like established a kind of a thing that different threads or core actually work together to compute a result, right? So those lanes are actually computing on a multiple data, right? Is that answer your question? So that's why we need to loop. So we are looping like for number of lanes, right? So this is the way it is not like looping. You have created 8 lanes. If you could remember the diagram, we were like hand coding. So we built those lanes, right? Two, three, four. So so each lane has adder, subtractor, multiplier, or XOR in this case, for example. It could be like more uh, if you have more options in terms of functionality in those lanes, right? So it lanes means you practically have 8 parallel hardware to compute those operands. They will come into those 8 lanes, and each lane computes results and gives it back to the register file. If both operands bits are all ones, then what will be the result of addition over here? It will be what it is. It will overflow, right? So those all kind of functionalities you could add. Uh, Overflow, even you could add the flag or something like that. So that's what I'm saying, that this is the simplest form we are building. So whatever the op A plus op B is doing, it is staying, right? So, okay, so now let's move towards the register file. So let us have that register file dot sv. You would create that file, and let's put it here, right? So so let us break this register file. So we have like some of the parameters here. So what is practically happening is that now each lane has its own register bank or array, right? So this is very again, this is the simpler way to write this. Otherwise, there is a lot more. You could say logic could be added to this, but again, in respect of the time, we will be just going through the simpler versions. So what are different things is that what are the number of lanes, parameters, and then how many registers you have per lane or per thread, right? And then what is the data weight of each register, uh, which will be the same data weight that you are calculating for those operands, right? For example, if you want to have 32-bit registers, means you will be calculating and operating on 32-bit numbers, right? So that's where you define the data width, and then there will be the address width. So address width will definitely depend on the register count. For example, if you have 8 registers per lane, you have like dedicated 8 registers per lane. So it means then you would need 3 bits for address width. Okay. So giving the parameters here. So if the number of lanes are 8, register count, if you're taking the register count of 32, data width is 32, and address width is obviously log 2 of register count, because whatever the register count is, you could take log of 2 and calculate the number of address widths. For example, in this case, the register count is 32. You have 32 registers per lane, right? So what does that mean is you need 5 bit of address width. Okay, coming into each. So now let's come to the ports of the register file. So first of all, you could see the RS1 and RS2 addresses, right? So these are primarily the addresses of the registers from which we will be fetching the operand A and operand B, which you just saw in the symbol value. Okay, but you are seeing that RS1 address and RS2 address also are shared across names, or they are not like dependent on the number of lanes. Why? Because again, the RS1 and RS2 address actually is coming from the instruction, and the instruction is same for the same the lanes in the same you could say warp, right, or the same thread, right? So RS1 address and RS2 address will be reading from the same register, but the data will be different. If I'm gonna where is this? So here you could see read data, read outputs data. So RS1 was same, RS1 address and RS2 address, but the RS1 data and RS2 data will be divided into lanes. Means, what does that mean is, it means that, so let's build it in the let's visualize it in using a block diagram. So let's erase this one. So let's erase this one board, and then we'll what is our register file doing. So let's do this. So for example, this is the register file. So what was happening was, in terms of read addresses, so we have RS1 data and RS2 data coming into it. Okay, so this is RS1 address for that what, right? So this is address, and this is address for B, right? And then this RS1, when data being read, it is being divided into now 8 lanes. Okay, so this will be like this one. When you're reading it out, so this is 1, 2, 3, 5, 6, 7, 8. Okay, so let's use this. So now you are reading operand A as 8 lanes or 8 threads of data, right? Because this register file is being uh, like used per lane, right? And again, for the operand B, you have 8 lanes coming out of register file, right? And you are reading that data in that way. So this has to be otherwise. Okay, and similar is the case for the right thing. So we have the simple address, the right as well. Right address is also a single address because it's coming from a single instruction. Okay, but again, the right data is again coming per lane. Each lane is outputting its data and writing it by register. So register's own portion, register files. So there are portion inside the register file that will have better handling each lane, right? So those parts of the register file are being assigned to that lane. So again, this data comes write data. If you are gonna write it into the register file, it will come from lanes. That per lane data will come in, uh, like we were saying it. So if we do this, we could say this is coming like this one, right? From ALU's 8 lanes, and this will be like, so it is coming into the register file, but the write address is the same. Write address will be a single register, right? Address. So this technically means that now register, the size is now a lot more, right? There are bigger registers now. The register file is now quite a large unit, right? So then if we have lanes, how we divide that register file is, we have now the data width, which is the size of one register. For example, if we say that single register is of 32 bits, right? And then we have register count. What does it mean is total number of registers, right? And then total number of lanes. So that register file will become like a 3D array kind of thing, right? So we will have like this kind of a thing. So this will be the register file, and then you say that you have, right, you say that you have, for example, 1, 2, 3, 4, 5, 5 registers. Let's say 5 registers. Okay. So you have 5 registers, and each register has 32 bits, right? And then you say then those 5 registers are being divided into 3 lanes, let's say, which means you could say, so this is So now, so you have one, two, three, four, five registers, and now each block has 32 bits of data. For example, if the data width is 30 bit, if you have now different number of data bits, so you could have different number of bits in this. So now each square is of 32 bits, and you have five squares in this lane. So for example, this is lane 0, right? So this is how your register file is now being divided into the lanes. For example, now this is lane 1, and you have register 1, 2, 3, 4 as well in this lane, and then you have lane, for example, lane number 2, and then you have similar number of and each register data width or the number of bits it is storing is 32 bits. Okay, so this is how this register file looks like. So again, the write and read logic is quite a simpler one here. It will loop through two variables, name and the register count. And again, I'm emphasizing this. This is not the complete, you could say, featureful kind of code or the micro arc we are looking at, because we cannot look into everything. But we definitely will be covering that in the training part, where this logic will get quite complex, and then we'll be deep diving into uh, every like you could say module, so that we have quite a real kind of a GPU there. Okay. So here you could see this is the number of lanes and the register count. So for example, if I have to access this register one, this one, right, this register. So what I have to do is I have to first address the lane, right? I would say, okay, go to lane number one, and if I come into the lane number one, then I definitely will say the address of the register, right? I will have to tell the address of the register, then the register address will be one, right? So what does that mean is that we have to first provide the lane number and then the register number, right? To access any register in the register file for this design, right? Okay. So that's why there are two loops. First is like accessing the lanes, and then the registers within that lane. So we are resetting those, and then if we are gonna write the per lane, right, we have to do that again, this loop, and have to check if there is a write enable for that lane. And if it is, then we have to write to that address. And similar with the read logic, so this read logic is again very is more simpler form we could do. Uh, Again, we are providing the data with the, so this is RS1 data is being accessed using the main, right? So RS1 and RS2 address are coming from the inputs, and we are saying that okay, send data to lane number 0, for example. Send read data to lane number 0 from register file uh, lane number 0 and RS1 address, whichever it is, right? So just send it to it, right? So it will send. So whenever this loop goes on, it will fetch data for different uh, lanes, right? For example, if this else value is 4, it will set the data for lane 4, RS1 and RS2 data from register files number of lanes, right? Any question on this logic? register file now. Any questions from you guys on this one? So if there are no questions, we can now move to the next question. Uh, Can we do like this that we made memory file and read this register file for operands? We made memory file and read this file in register. So I didn't get your question. Maybe you could uh, elaborate a bit. Yeah, by lane means ALU lanes, right? Yes. So now let's look at the warp scheduler a bit. So this is again quite a simpler version of the warp scheduler that we are going to see here. So what does that warp scheduler does is it, let me create the file first. So try to warp and name it warp scheduler.sv, right? So a warp means that you have dependent instruction going into that warp, and there are group of codes or lanes you have to execute that result, right? So this warp scheduler actually sits in the hardware to actually control the warp. So, for example, if some lanes or the SIMT ALU is busy, it will definitely have to get that instruction to some other warp, right, to compute the results. So, for instance, it will have like warp IDs. Okay, so those warp IDs will definitely define that which warp this uh, instruction has to be routed, right? For example, for this warp scheduler, the logic is very simple. So first, it will check that if some warp is ready, and it will come from scoreboard or memory type. Okay, because scoreboard will be checking those things as we discussed in the slides part as well. The scoreboard checks for the any dependencies or checks if any register file if any register is like busy and the computation is ongoing, right? So if it is the case, it would say that warp is not ready, right? For example, uh, there is computation going on in warp 0. The ALU is busy with all the computation. So now scoreboard will indicate the warp scheduler through this signal warp ready that that warp is not ready and do not uh, give the next instruction to that warp, right? Why not we are forwarding in this fetch file? Yeah, we could have added the register file, sorry, the forwarding in this register file, but we have skipped for simplicity, right? If you would remember, the last register file that we discussed in last session has that forwarding, but for this one, it is not there, right? So that's why when it was like reading, I was going through the read logic here. So I said that this is now the simpler logic for the read. Uh, okay, so it could cause issues, but yep, we 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 haven't added that into the register file. Okay, so this warp ready will indicate to the warp scheduler that some specific warp is uh, busy, right? So let's look at the logic here. So again, this is a simpler form of the warp scheduler. We are skipping part about more features actually, so that we could uh, understand somewhat this hardware in this short form time, right? So what will it do is it will loop through the number of warps. For example, if it had 4 warps, it will loop through them and check for the warp ready signal. So logic here is round robin. Okay. So what does that mean is it will go through the circle, right? For example, it will send the instruction to warp 0, and then if the warp 0 is busy, it will send it to 1, warp 1. And if warp 1 is busy, it will send to warp 2. And if warp 2 is busy, if it will send to warp 3, even though warp 0 is also free at that point of time. Okay. Even though warp 0 was free when warp 3 was free. Okay. But because it is following a round robin kind of a policy that it will give every warp the chance to do that competition and not go again from the start of the index, right? So if it checking at index 2, this means that warp 2, and if warp 2 is busy, it will send the next instruction to warp 3, not warp 1 or warp 0, though they are like uh, free. So that's why it circulates equally through all of the warps. So this is one implementation. There are other implementations as well for this one. Other so we could definitely use them, and and we could be going through it in our training as well. Okay, so okay, so no, those that .mem file is not equivalent to the registry file. Okay, so that .mem file is the memory thing, right? So register file is, so how could you divide the .mem file into like bank register, right? Okay, and that is what. So it will, so this IDX will get the next index. Okay, and then it will check that index. If that index warp is ready, When warp 2 is ready, it will send that index as the warp ID. So warp ID, what is the warp ID? Warp ID is the output from warp scheduler. Okay, so this warp ID will tell the unit to send the instruction to this warp. For example, it generates warp ID 2. So it means now the instruction will be routed to warp ID 2 or the warp number 2. And it will send the valid one signal with it so that there's no garbage data going on. Even if there is no valids there and warp ID will be there, so it doesn't compute anything. So there will be valid going on with this. So this is how the warp scheduler will schedule the warps for computations. Okay. Any questions on this one? So if anybody thinking that where does this warp ID will go, it will go to the scoreboard. Okay. So in scoreboard slide, we have gone through that scoreboard. It choose the instruction. It will check if some register is busy or not. And if it is busy, then in third step, it will check if it is released or not, right? If it's free or not. So scoreboard will be telling the warp scheduler that some specific okay, let me draw that diagram there. So this is important to understand here. So let me so for instance, if this is a warp scheduler or let me make it somewhat smaller. So this is a warp scheduler. This one and this one is the scoreboard. Let's say, and then there are a number of warps actually, or to which the instruction is to be sent, right? For example, in this case, there are two. Okay, let's assume it for the simplification. So what will happen is this scoreboard will tell. So this scoreboard will be sending 2-bit signal now to the bar. Okay. So if you could see here in this code, this warp ready signal is equivalent in bits. Size is equivalent to the number of warps. So that each bit is representing some specific warp. Okay. So it is sending ready signal. Okay. So it will tell the warp scheduler. For example, there are two warps. Okay, so let's say this is warp number 0 and this is warp number 1. So for example, it is saying so it sent uh, 0 and 1, right? So there will be 2-bit ready signal going to the schedule, so warp scheduler from scoreboard, right? So this is scoreboard. Okay. So what does that 10 would tell to the warp scheduler is 0 means some warp is not ready. Okay, let's assume that. So it will assume now that warp number 0 is not ready. Means this scheduler, sorry, this scoreboard had issued an instruction to this warp 0. Okay, so now this warp 0 is already computing some instruction, so it is busy right now. So this is you could see, so this is busy, okay, and this one is free. So this scoreboard has now sent warp scheduler this signal 10. So now warp scheduler knows that warp 0 is busy, but warp 1 is ready. Okay. So here you could see. So this warp ready signal has come, and now this warp scheduler knows that okay, warp ready for 0 is down, but for 1 it is 1, right? So for warp 1 is ready. So what will it do? So it has an output which comes to the scoreboard with the name of warp ID, warp warp ID. Okay. So this warp ID signal will tell the scoreboard that now which uh, warp it should send the next instructions. For example, let's say that we have now three warps. Let's assume it's number three. So let's say now scoreboard sent 110, right? 110 means warp Z. So what will it do is it send the warp ID. So what will it do is it send the warp ID equals to 1 equals to 1 warp ID equals to 1. Okay, it will send warp ID equals to 1. Okay, so warp ID equals to 1 will come to scoreboard, right? So now scoreboard knows that for the next instruction it needs to send to the warp ID 1. So it will be connected to all the warps. It will send to 0, 1, 2. But now warp scheduler has told the scoreboard to issue the next instruction to warp ID 1. So this instruction will now flow to warp ID 1. So okay. So once this goes to the warp ID 1, and let's assume that warp ID 0 and warp ID 1 are both busy. What will happen is now scoreboard will send this ready signal not as 110 but as 1, 0 and 0. What does that mean is now warp 0 and warp 1 are both busy, and warp 2 is random. Okay, understand now? Does it make sense? So next we will see the scoreboard. Okay, so how this warp ID goes into the scoreboard and how the scoreboard actually checks for the conflicts between different registers. Any confusions or questions on this one? Does it make sense now? Make it does it making clear? Okay. Any questions on this one? Otherwise, we'll move to the scoreboard part. Okay. If there are no questions, then I guess we could move to the scoreboarding part. Uh, Again, that scoreboarding part has been like implemented in the most simplest way so that we do not have like because this is a lot of code actually, and if you are gonna cover it in a single session, it will take a lot of attention, and it will really be a difficult task to grab all of the concepts. Okay, so that's why I have like tried to simplify it as much as possible so that you could get the concept out of it, the main concepts out of these blocks actually. Okay, Otherwise, in detail, RTL, you could say, would be covered in the training part, and that too will be like a 5 weeks long training. So it will be a good time to dig into each module and know about the RTL and how to code them and what features are available and what how can we do it. Okay. Uh, so let's create a scoreboard file. So now scoreboard.sv. Um, so if you have any confusions till now, you can ask the question. Okay. So there is no you don't need to be hesitant about that. You could ask the question so that at least you have like a good picture of what's going on, right? You could connect the dots uh, between different modules and different functionalities of this structure. Okay, so let's dig into the scoreboard now. Now again, now the scoreboard. Now the scoreboard has an input warp ID that we now parameters. Okay, so scoreboard needs to know actually two parameters for this design actually. So first parameter is the number of watts. Okay. So number of watts mean that because it is gonna schedule the instructions to those watts. Okay. So and second one is the reg count. Reg count because it needs to check for the conflicts between the different registers that we talked in the slide part as well. If you could remember here, let me share that once more. That's good. So here it needs to check if some register is already being used as a destination register. Okay. So it needs to know how many registers are there. For example, if there are 32 registers, it will be like locking those registers in between in those numbers, right? It will implement the logic for those many number of registers. So then the first input is the warp ID that is coming from. So that warp ID is coming from a warp scheduler, which is telling the scoreboard to which warp it needs to send the next instruction, right? Then there are a bunch of inputs that are coming into it. Okay. So this is the issue valid. So issue valid means so it is coming at which uh, for which RS1, RS2, RD the instruction has been issued, right? And then it gets the write back valid. Why it needs write back valid and the issue valid? So the issue valid is required so that it knows that which RD is being logged right now, right? Okay. And the write back valid will tell it that now that destination register is being freed out. Okay. And it has a single output stall. Uh, in this case, but uh, I guess there is missing logic as well, which is the warp ready. Okay, so let me put that into as well. So it requires the output logic, and that would be equal to warp. So this is capital warps minus 1 down to 0, and okay, so this is warp ready signal. Okay, so it needs to tell the scheduler back that it that which warp is actually ready. So So it will create a busy signal logic inside it so that it knows which one is busy and which warp is not busy, right? Okay. So here is the its logic actually, uh, which is like quite simpler one. So how it calculates is it checks for the issue valid. Okay. If there is an issue valid, it goes to that warp ID, which because this is a 2D array, okay, this busy signal. So for 8 warp IDs or the 8 warps, you could say it would have like 8 lanes, okay, okay. So and the register count will tell which register is to be logged, right? So what it will do is if issue valid, so it what does it mean is some instruction has been issued, right? Okay. So some instruction has been issued. So the destination register of that instruction going to some warp ID should be locked, should be busy, right? Okay. So now, as long as the it is busy, now next instruction cannot write to this destination. Okay. And if the write back comes in, okay, okay. So if the write back when it comes in, so now you make this busy signal zero. It means the destination register is now free. Okay. So same in same way we can literally put that var ready signal as well here, but we need a different loop for that because we have to loop through now the warps. Okay, so we can loop through the warps and send the warp ready signal back to the warp scheduler. Okay, so you could add the warp ready logic in here. Okay, any questions on this one? Okay, let's let's now move to the next. So will you be sharing all the code as well? Yep, we'll share that in a repo. So, so the code repo and the slides of the today's session will be shared actually in maybe 1 or 2 days from now on, because this code hasn't been tested for the compilation issues. So I will send after the compilation is is error free. Okay. So any questions other than this? Otherwise, we move to the next module, which is the execution model, which is like handling the warp level things. So we will discuss some divergence concepts here as well, so that how it could be handled by the code. So first, if there are any questions at this point of time. So let's take a 5 minute break and then we'll come back. Okay? Just a 5 minute break to freshen up and we'll be back. Okay. Thank you. So, okay, let us get back to our session. Am I audible? So let's now look at the logic actually to create the active mask first, uh, and then the PC out. We have like uh, gone through the PC, and now we need to fetch the next PC, right? So that logic has to be there. So let's move to the. Can anybody confirm that I'm audible? Right? Okay. So let's put this model into this. So we have execution model actually for SIMT, which is, you could say, that controlling a number of things. First one is the arm warp kind of active mask that we were looking at, that which lanes are active, right? And then manages the divergence as well. Divergence actually happens when there are branches. So that information to it comes from the code, if this is a branch instruction or not, and then it uh, implements the logic for divergence and convergence, etc. And and then it moves the current PC back to the instruction fetch, and for fetching the next instruction as well. Uh, so one of the things that we not implemented yet in this one is the warps one. Okay, so this one is for the single warp. Okay, we could have to just add the warp signal into it in terms of sizing, so that it is looping through the warps as well. Okay, uh, so let's look into it. First thing is coming into it is the PC, just coming as an input, and it will take one cycle to output this PC out, right? To the next, that's the next instruction. This is the logic for this, that it has to calculate the next. PC out of it. Okay. So by default, it is the current PC is the PC in that needed to be fetched. Okay. Uh, so with the next instruction is to fetch. But in the case of branch divergence, it needs to be calculated when there is a re uh, convergence info and all that stuff to be taken into account. And then the current PC actually becomes the branch target. Okay, so the branch PC, uh, the PC that is being calculated after the branch. So there is okay. So this is the PC state for it. So by default, if there's no branch, so PC in that input PC is the current PC that is being like moved after a cycle. Okay, but if there is a branch, there is a divergence. You have to calculate that branch PC as well. Okay, so there you're seeing a bunch of signals for the branch one related to branch. We haven't covered much about the branches in this workshop actually, in terms of divergence or that stuff. So, so these signals usually come from the decode stage, which will tell the this execution unit to branch valid and there is the branch target and all that stuff. So, okay, and these branches are primarily actually, if you could look here, so if there is a branch valid, which means now there is a branch, okay, so it has to handle that divergence, and there will be like couple of masks. First one will not taken mask and the taken mask, okay, so that will be calculated from the branch masks that is coming uh, from the decoder side, okay. I guess if I'm going through this, it will create a lot of confusion for you as well. So let's remember that the divergence is the part whenever there is a branch, so you have to have some of the lanes active for one part and other one for the other. Okay, so you need to have mask. Okay, so uh, that mask is being calculated here, and then it waits for the reconvergence. So reconvergence means that now the branches has been resolved actually, and then the divergence path is completed, and now you are back to your uh, regular calculations. So here it is using the stack pointer kind of a technique. So what it does is it really pushes those, because we know that for one set of mass, one set of lanes would be active and other ones will be inactive, right? So we need to use the stack pointer, okay, and have to push the information which is required for the reconvergence. Uh, so that when both the paths from the convergence are being finished and we have done operating on them, then we need to have that information here with us related to reconvergence. So that reconvergence part could be like put into a register, handling it, okay. So it will involve the mask and the current PC information, actually, because in the case of divergence, there will be two PCs. Uh, one will be for the taken and one will be not taken. and then it calculates the divergence path, and once that is done, we are left with the reconversion, and we can pop the results from the stack and back to the PC. Okay, and we get the mask for the lanes as well. For which lanes we have to put the mask. We have to like mask out those lanes, which we have seen in this SIMT area as well. If you would see there, this active mask part. So this comes actually from branching part, and specifically uh, calculating those masks, and then this execution model puts that out active mask and the PC out to the output, right? So this topic needs to have like more discussion and more depth to actually understand it better. Uh, but I'm just giving the overview that so that at least you have some idea that there's and there are branches. This is a divergence path and then the reconvergence path as well, and active mask calculated out of that and PC. Okay, so this is the execution uh, of the model of the execution module. Any questions on this one? The time is just running out, and we have like minutes left. So let me. So we'll share this working code with you guys as well. So if you have any questions after that as well, we I guess we all are in the WhatsApp group as well. So you could ask the questions there as well if you have any questions out of this related to this code or today's session, or even about the whole workshop. Okay. No questions. So, so we have already covered much of the like the functional modules which are like working in the CMP core as well. So the major logic you could say we have simplified it a lot actually, but we have discussed that. So now the major thing is to just connect them into a top level core and add some of the pipelining structure into it. Okay. Uh, so I guess now the time is just because I have to move to the next meeting as well. So the few minutes left. So let's. So major modules are these. Now just need to connect those into a core and have that running in a test bench. We'll provide that code to you. Okay. To all the workshop attendees in the through email and WhatsApp as well, so that you could run it and see yourself in the waveforms, what's happening. Uh, but be mindful of the thing that this is very like simpler form of it. So, but in the training parts, maybe you could ask overall questions. Maybe you could ask overall questions as well, maybe related to industry as well, because I'm seeing a lot of students in there as well. So if you have any kind of questions or any kind of related to GPU or overall uh, thing or any confusions, we can discuss that, because if I start to go through that connection part, so it'll I guess it will not be completed. And we have covered the functional units and major blocks. So you can definitely look at those and try to revise that and code themselves. So yourself as well to better understand that. Okay. Once we have shared the repo code with you, and then along with the, you could definitely add more code to that, or try to experiment with the code and then have fun with it and happy learning. Any questions on your part? I can understand that it will be a lot in terms of, especially in coding, because you so our style in coding is actually that we first go through a micro arc spec and diagram first for that module. Okay. So our usual way of having these codes is that we go through micro arc specs with diagrams of that module, and what that module is connected to which modules, and it is communicating to which modules and the RTL stuff. And then we then like go to the decisions, design decisions, that why some certain decision is being made, and how can we like make the other decision, and what would affect the RTL. Uh, so first we go through that discussion, and then we come to the code. Uh, if so, but for this workshop, actually, it is not possible because the time constraint and all that stuff. So we need to just go through the code and overall picture uh, of the RTL and how the things are going. Uh, so if anybody of you are interested in training or in that stuff, you will definitely feel more comfortable with that, because the pace and the time will be like ample to go through every detail of a single module, and then uh, discuss it in detail, and even add features to really replicate it as near as possible to a real GPU, right? So last couple of minutes to the session. So if any comments, suggestions, or questions, you can definitely add up. And yes, your certificates will be issued tomorrow, right? Okay. Of the workshop attendees, your certificates will be issued tomorrow, and I'm hopeful that the code base and will be ready by tomorrow, and we'll send that as well. Okay. So any questions, any feedback, any suggestions, anything? Yes, the training is actually paid. Yeah. Good. Yeah, we can definitely look into it. So this is to be so okay. If there are not any other questions or suggestions or feedback, you can definitely give and ask questions in the WhatsApp group as well. You all guys are there. So let's wind up for today's session and let's connect. Let's be connected for the next wave of workshops that are coming and learning and all that stuff. We do intend to announce internships in mid June as well. So maybe we'll cross our paths there as well in building and learning RTL and verification and stuff and doing something good stuff as well. So let's hope we'll meet again and then do some great stuff. Oh, thank you, happy learning, and it was great to interact with you guys. And you were really super energetic and really were very, uh, you could say, motivated. So really loved the energy and so if anything else is like missing from our side, with you could definitely give us the feedback as well in the feedback form and even directly through the WhatsApp messages. So uh, we'll love to remain connected for our you could say for learning and all that stuff. So in the future.